Okay, I think we'll begin. So welcome everyone. Today we will provide some clues on how to enhance embedded HVDC links control to improve the security of hybrid AC-DC power systems. So with me are my colleagues Antoine and Juan Carlos, which will help answering to this question. And they are both HVDC system experts at the Institute, and they work as research and development engineers here. So Juan Carlos is working in power system stability in hybrid AC-DC systems, and Antoine works in the real-time modeling and simulation as well as HIL testing of control and protection systems for HVDC grids. So a few points about this webinar organization. First, we are recording this, so it will be available for replay in our YouTube channel afterwards. And all attendees' microphones are muted by default, so we don't hear you, but please write down any questions you may have in the chat. All these questions will be answered in the Q&A session at the end of the presentation. So for the next hour, what we propose is the following agenda. I will start with a short introduction on the topic. Then I will hand over to Juan Carlos, which will explain you how to enhance transient stability of a power system by means of control-based solutions using embedded HVDC links. Then Antoine will explain how this solution can be implemented using existing vendor equipment and show some results of the HIL testing of this setup. And finally, I will come back for a wrap-up and host the Q&A session at the end. So let's begin with some context on our work environment. We work at the SuperGrid Institute, which is an independent institute that is developing HVDC technologies and expertise. We focus on all aspects of HVDC systems, including the architecture design to study functional and technical specifications of HVDC grids, control and protection. And the work presented here today was done by this division. But we also focus on HVDC technologies such as power electronic converters, the substation equipment for interruption and insulation of DC currents, in cables, and storage systems for future hybrid AC-DC grids. So through our high expertise and cutting-edge testing labs, we are actually becoming a leading actor of future HVDC grids. So some numbers to back up what I just said is today we are almost 170 collaborators, and almost 1/3 are PhD students. Another interesting fact is that we gather almost 30 different nationalities, which makes the work environment very open-minded and dynamic. We are active in scientific and industrial communities as well, so a number of publications and patent claims. We have worked with several partners under collaboration frameworks, providing consultancy on testing services. So today we present two ways of partnering with industry. On the first part of the presentation, Juan Carlos will talk about the collaboration with Red Electrica. And in the second part, Antoine, a partnership with G Digital. And they will talk more in depth about what we did in these partnerships. So to give you some context of today's topics, as you may know, HVDC projects are flourishing in the European landscape. So the application we present here today will fulfill the requirements of a power system where embedded HVDC links are located. So an embedded HVDC is an interconnection between two system areas already connected by at least one AC link. There are many existing and future links corresponding to this characteristic in Europe, such as the several interconnections between France and Spain, the France-Italy interconnection, all German corridors, but the length of such corridors may require further investigation to decide if it's embedded actually. And even some UK links I know of, and so on and so forth. So we can only expect more of them coming in the future, because there is a need for better European interconnections with HVDC that offers actually lots of flexibility and can be solution for bottleneck issues in the actual system. So This high volume of HVDC links and maybe multi-terminal links in the future have been identified by the TSOs as a challenge that need to be addressed by research, development, and innovation. So the NSOE, which consolidates the view of European TSOs, mentioned in its latest RDI roadmap that to enable secure operation and of widespread hybrid AC/DC grids, RDI must focus on these milestones over the next 8 years, as you can see up here. So the topic presented here today is in line with milestones related to AC/DC system modeling, controllability and stability assessment, and understanding the interactions between AC and DC parts of the system. So with that context, let's welcome Juan Carlos to present the next part of this webinar. Please, Juan Carlos.
Okay, so thank you very much, William. Okay, so thank you very much, William, for this introduction. My name is Juan Carlos Gonzalez, and in this part, I will present you the experience we had collaborating with the transmission industry, and more in particular with the Spanish TSO to provide innovative solutions to actual TSO challenges. Okay, so I will start presenting the particular problem that we treated during this work. And this is probably something you are already familiar with. As reported by ENSOI on the 1st December 2016, an unexpected opening of a line in the French system triggered an oscillatory incident in the continental Europe electricity system, where actually a 0.15 Hertz oscillation appeared, in which the Iberian Peninsula was swinging in antiphase with the rest of the Central Europe system. This natural oscillating mode in the European system is known as the east center west mode. And during the oscillation, actually, the biggest amplitude was registered on the Iberian Peninsula. Okay, so if we took a look to the interconnection between France and Spain, we can see that it is actually a hybrid interconnection. We can see that we have some AC lines between France and Spain, and also we have the INELFE HVDC interconnector in the east part of the system. The particularity of this HVDC interconnector is that the active power control is selected to operate both converters using the angle difference control, also called AC line emulation. This control measures the angle in both the stations, the phase angle of the voltage, and applies a gain proportional to the difference of the measured angles. A filter is used to suppress this noise of the measurements and reduce the effect of some communication delays. This is the filter. This control is very useful for TSOs because it allows the HVDC to adapt its power flow reference to a natural pattern of the power flow along the interconnection. So if the power goes from Spain to France, then the angle difference control will adapt the power reference of the HVDC to go from Spain to France. And therefore, the ADC reduces a lot the TSO intervention in the redispatching process of the HVDC link. Following the analysis and some studies in the behavior of the INELFE HVDC link during the event of 2016, both TSOs, Red Eléctrica and RTE, proposed a modification on the tuning of this controller. And actually what they did is that they slowed down this filter, and they changed the time constant from 0.75 to 50 seconds. And what they did was therefore to slow down this filter, and as a result, we have an oscillatory behavior of the whole system that was enhanced. And but also, I mean, in the other hand, we have that the fast dynamics of the HVDC are not fully exploited. So if there is a disturbance in the system, as we have a slow filter, the HVDC is not going to react very, very fast. It's not going to adjust the power set point very fast. So, well, thanks to the collaborative program Grid 2030 with SuperGrid Institute, we had the opportunity to collaborate with Red Eléctrica via the RIDSE project. And in this project, in order to analyze the system behavior, it was proposed to receive the modified dynamic study model of the continental Europe in PSCC, you know, this complex dynamic model from Red Eléctrica, in which they managed to reproduce the oscillatory behavior. Well, we analyzed this model and we proposed to reproduce this oscillatory behavior on a simplified benchmark, where we reproduce the interconnection between France and Spain, and we represented these two areas by two IEEE benchmarks. In this simplified model, we could analyze the problem and then propose solutions. And at the end of the project, we applied these solutions to the complex dynamic model. So the interest of the approach, of course, is that we can provide generic solutions that are not only applicable to the France-Spain interconnection, as the system is not exactly the same, right? We reduce the complexity of the system, so therefore we can add some detail on the components we use. For example, in this project, we use EMT simulations on the reduced system. And of course, we can avoid confidentiality issues since we are not using actual grid data. If you want to publish the results, it is possible without putting at risk any confidential data of the TSO. So if we take a look into the detail of the control, as I said before, this is the current controller that is used in the HVDC link, in the INELFE HVDC link, in which we use the angle difference control, and is mainly used for steady state purposes. We want to adapt the power flow to the natural power flow of the system, right? But as observed by Red Eléctrica, and as I said before, this fast filter does not contribute to improve the system damping. As we can see in the blue curve, we see that the system has an oscillation that is not well damped. And in the other hand, when they slow down the filter, this the oscillation damping was improved. However, we can see that the HVDC contribute less to a transient stability. You can see all this gray area is not really used. It's kind of a shame because the HVDC link can react very, very fast, and we are not using all this gray area. So we identified this as an area of opportunity in which we can provide some solutions to use this fast response of the HVDC link. One of these solutions, or one of the things that were already tested by the TSOs, is what they call the PPOD, or power oscillation damping, in which the principle is very similar. They measure the frequency at both stations, and they apply a proportional gain to modify the power reference to apply damping to the system. This is a very well-known solution. It's not the only way to provide damping of the system, but it is a very straightforward manner to do it. The problem with this particular control is that the topological situation of the HVDC link made that the frequencies measured at the connection buses of the HVDC link provide very little information about the oscillation. So the points of connection of the HVDC link are very close, electrically speaking. So if you want to apply some important control actions, we need to use high control gains, right? And if we use these high control gains, we observe that they can lead to instabilities, as the yellow curve suggests. Okay, so we identified these two areas of opportunities, and during this RIDSE project within the Grid 2030 Innovating Program, we proposed this third action, which is more focused on the transient stability of the system. So the idea was to work together with Red Eléctrica to propose an action to exploit the fast response of the HVDC link and to validate these propositions in simulation in the complex model, in the dynamic complex model. Okay, so regarding the first proposition is what we call the trigger power compensation, in which we want to take advantage or to profit the fast dynamics of the HVDC link compared with the AC grid, right? We propose this action called the triggered power compensation, which is a very intuitive action in which if we detect the tripping of a line or for a generator, a signal can be sent to the control. We apply this kind of impulse, this supplementary power profile, and the HVDC link can apply this power. So, for example, here in the interconnection, if we detect that we have a problem on one line, this line is tripped, and we can communicate this to the HVDC link to apply the supplementary power profile. And therefore, this power profile, as is triggered when there is a problem, it reallocates the power of the lost line or generator on the HVDC way faster than the ADC that has been already slowed down. And something that was very important for us is that this power profile converges to zero. So in a steady state, the value is determined by the ADC controller. And this was a requirement from Red Eléctrica. They wanted that the steady state active power is decided by the angle difference control. Of course, it's quite evident that the challenge that this solution has is that it requires to detect the event and communicate the event to the controller. Then we have another proposition. In case we cannot detect the problem, we only observe that the system is moving after some event. We cannot identify this event, but we can still do something, right? And what we proposed is instead of taking measurements of the frequencies at the points of common coupling of the converters of the HVDC link, we can go inside the different areas, right, to take measurements of these frequencies, and then we have more information about the oscillation. And if we have more information, we can apply, let's say, most aggressive control actions and more efficient control actions also. So we take the measurements of these frequencies, we can calculate an average frequency of each area, and then we apply, of course, a gain. And it's important to have a deadband in this gain, because we only want this action to activate when there is a large disturbance in the system. Okay. So as I said, in case the trigger power compensation is not applicable, we cannot detect the problem, this frequency activated action still enables a fast response. And the deadband allows to use frequency measurements of remote buses and make sure that the modulated power is always in the right direction. Again, the challenge is that we require a robust communication system, a wide area communication system to apply this kind of controllers. Okay, so we finally propose to apply all these actions in the HVDC link, and this is actually what we call DVAC here in SuperGrid for dynamic virtual admittance control, in which we can see we have the action of the emulation of an AC line or an admittance, and we add some supplementary dynamics to enhance its behavior. This is why we have this name. And we can see that these actions, the four of them, are quite complementary, and therefore they can be implemented piece by piece if the operator wants. The next step in this work was to apply this control on the complex dynamic system on PSCC. So again, together with Red Eléctrica, we implemented this into the dynamic model of ENSOI, which was modified to represent the oscillation of 2016. And in the first plot on the left, you can see that we have what we call the base case, where only the angle difference control is implemented with a slow pass filter. And you can see that in the simulation, after the event, the event was the disconnection of the line, exactly as it happened in 2016. So we have the disconnection of the line at the beginning of the simulation. And then we can see that the HVDC link in purple takes some time to arrive to its steady state value. However, the parallel lines, which are the blue and the orange ones in the France-Spain interconnection, they reacted quite fast and with very high peaks of power, right? And this is again caused by the fact that the HVDC link is not reacting faster. Then when we apply the algorithm that we propose, we can see it's very clear that the purple curve, the HVDC power, acts very, very fast. I mean, we trigger the power compensation, and we made the hypothesis that we had information about the perturbance, the disturbance. We knew which line was open, and we react accordingly, right? So we have this first impulse in the HVDC power, and then we modulate the power to compensate the oscillations. And the most important thing here to observe is that the power peaks on the first swings of the parallel lines has been reduced a lot. This is very important for operators, and for the electrical it was very important because this reduces a lot the probability of any protection on those lines for tripping, right? So we reduce also the probability of having a cascaded event. In the next slide, we will see how the different actions of the DVAC control act to create this purple curve. So if we decompose this action, the power of the HVDC link into the control actions, we can see that we're going to have the 4 control tracks: the ADC, the POD, the trigger power compensation, and the frequency activated action. And we can see that the angle difference control reacts slowly and then goes to a steady state value at the end of the simulation. Then the POD only applies power proportionally to the frequency difference. Then the trigger power compensation, we can see that we apply this impulse and it tends to 0 at the end of the simulation. And we have also the power of the frequency activated action, which is in phase with the POD, but we have also these dead bands in which the control doesn't act, because we wanted the control to act only in case of large disturbances. Okay, so these 4 actions together create the active power that we observe in this curve. So just a quick wrap up on this section. I mean, it is very straightforward. We managed during this work to work together with the transmission industry to understand and reproduce their technical issues, and of course propose collaborative solutions. The algorithm that we propose, which is called the Dvac, is accessible to all TSOs. We say it's accessible because it represents a sum of complementary actions that are quite intuitive for TSOs. And it is very important also to say that this solution can be implemented piece by piece. Each action can be implemented separately in the HVDC link. And then a third, last point, which is is not really a conclusion, but it's something important to remark, is that all these concepts are fully compatible with multi-terminal DC grids. As we saw in the introduction, where there is this tendency to have more interconnections, which will lead at some point to multi-terminal DC grids. And it's important to say that all these concepts can be applied on these multi-terminal DC grids. So this is the end of this second part. I will leave the floor to Antoine for presenting the next section.
Okay, so thank you for your insight, Juan Carlos. So now I will show you. So my name is Antoine Dvac. I'm an HCL engineer at SuperGrid Institute, and I will present you how we brought the DVAC algorithm closer to reality by implementing it in the phaser controller. So it is an industrial controller, thanks to a partnership with GE Digital. So first, let's see some things about offline simulation and real-time HIL simulation. So in an offline simulation, like Juan Carlos showed you before, we can see some inherent problem to this kind of simulation. So the algorithm is, of course, inside the simulation. So you will have an inherent synchronization between the controller and the models. And you don't have a need for communication. So the signal or the communication is, let's say, perfect. You have no delay, no problem, no loss. And so you don't need, let's say, to take into account the resiliency issues. In hardware-in-the-loop simulation, we will extract the algorithm and put it into a controller. So the model has been simplified because as this is a real-time simulation, it has to be the computation of the simulation has to be really fast to match the real time and talk with the controller. And we have now we need to take into account now the measurement, the measurement and the events that goes into the controller, and the controller need to feed back its outputs to the simulation. So for this, we need a communication protocol. So we will see that we use two industrial communication protocols in this setup. So first of all, we have the let's say the setup. So the DVAC algorithm implementation has been how do you say? The DVAC algorithm has been implemented into the phaser controller. So the phaser controller is an industrial controller. For example, we can find it into the France INTELLI-Link, and it automatically. The advantage is that all the resiliency issue are tackled by this kind of computer, and it automatically synchronizes data. On it, we add in the setup two communication protocols. So we have the IEC 61850, which is a protocol used for automated substation, which will be used for automated substation. And we transfer the active power modulation from the phaser controller to the real-time simulator. And after, for the synchro phaser measurement, so measurement coming from the simulated TMUs, we use the C37118 protocol. And as it is, as the DVAC use angle measurement, it is really important to have a really precise timestamp with a GPS antenna clock, because time error means phase error, and it is really important for DVAC. So how we implement the DVAC into the controller? So inside the phaser controller, we use directly software from GE called the Phaser Controller Designer. And this software helps us to program directly DVAC thanks to logical blocks, a bit like Simulink for those who know. And we have also option to monitor value of different variables during the simulation. And we use a mix between built-in blocks from the libraries of directly provided with the phaser controller. So more for phaser reception and management, like sanity checks and loss of data. And we built DVAC directly into blocks. So the DVAC can of course be implemented also with code directly implemented inside the hardware. So this is the scheme of implementation for the DVAC. So we can see the four parts that are linked to what Juan Carlos presented. So you have the angle different control, you have the power oscillation damping block, you have the frequency action control block, and you have the triggered power compensation loop. So those are summed, and also we put a rate limiter and a saturator for safety reasons to the output for the active power reference. So now that we saw that we can implement the algorithm inside the provided hardware, but our HCL platform is also able to implement this kind of algorithm directly on Raspberry Pi. It's an algorithm prototype on Raspberry Pi, because Raspberry Pi are now becoming more and more powerful and are quite cheap and offer a flexible alternative to industrial controller. So that's the advantage, that if we want now to test an algorithm in HIL without providing an hardware, we can. And we have some technical specification on this kind of controller. So this control, of course, this implementation has some drawbacks, things we need to take into account, but it's also some challenge we can solve. Is that we need of course to program everything in the Raspberry Pi, including the communication interface that need to manage protocol communication like ESA 61 and 50. And we need also to implement some synchronization function in order to take into account, for example, communications delay. And of course, all the real-time loops, all the function that will manage the real-time into the Raspberry Pi to manage a constant execution. So with this both implementation of DVAC, the message is that we can offer an HIL, an hardware in the loop setup that is flexible, and we can improve. We are always improving with our development knowledge. Here we show we can incorporate efficiently an algorithm in a test environment. So with a provided controller from a partner, or directly the ID of the algorithm in an hardware that we prototype. And the idea is that with the HIL capability we offer, we can also talk with you in your algorithm, because we have some HVDC and power systems expertise. So that was for the setups. Now I will show you some results about that we achieved with our setup. So I will go through 3 test cases. So the first one is a fugitive fault in a transmission line. So the transmission line is parallel to the HVDC link, and I will show you 2 test cases that are quite similar. It's the complete loss of the AC transmission lines. The idea is to show that the HVDC link is able, thanks to the angle difference control, to maintain the synchronism between the 2 areas. But in one case, we will have some constraint of the converter headroom. So this is the first test. So it is just a fugitive fault in the transmission line 1. The idea of this test was to test if we obtain the same result with the algorithm in the phasor controller and here or in the Raspberry Pi. So we can see that the results are similar. So for the angle and frequency difference, because as it is a fugitive fault, we can see that the triggered power compensation loop is not active there. So let's talk about the second scenario, which is an islanding event. So we completely open the AC transmission system. So here we can see that the breaker opens at 1 second. We can see the loss of synchrony with a constant reference converter, active power constant reference converter. We can see that we lose the synchronism between the 2 areas. But thanks to the DVAC algorithm, the HVDC link is capable via angle difference control and an instant power injection to mitigate the first oscillation, so the disturbance, the complete disturbance, but also after to maintain the synchronism between the 2 areas. So we can see if we reduce the capability to the HVDC to 300 megawatts, we can see, of course, that the algorithm doesn't have enough active power to maintain the synchronism between the 2 areas, but we can see still that we lose the stability around 2 seconds. Around 2 seconds after that, if we have a constant reference. So that means we have more time for external actions, and in AC system, of course, 2 seconds is a lot of time. So that's all for the results. Thank you, and I will hand over to William from the wrap-up.
So thank you very much, Antoine and Juan Carlos, for giving us these very interesting insights. So just to conclude this presentation, I propose slides. Yes, propose well, say what I understood of the main characteristics of the DVIC is that it produces a triple effect for the enhancement and of power system stability, which are synchronizing power that produces an emulation of an AC line behavior by the HVDC link, a damping power that reduces oscillations on the AC side, and the fast response that is the direct benefit of HVDC technology and that has no longer to be sacrificed to ensure AC system stability. So these effects, which are characteristics of DVAC, bring several benefits to TSOs. The main ones are using the embedded HVDC link to increase AC transient stability and security margins, to use information coming from PMUs and then additional control application to recalculate power references for HVDC link in a smart way that redispatches the power and can avoid power loops between the interconnected zones, let's say. And of course, in case of severe disturbance, the time constant of the DVAC generates a power response that is in no time to improve the transient stability. And finally, these three previously aforementioned effects that I talked before of damping, synchronization, that also enhances dynamic stability of the surrounding AC grid. So this is it. This is the final slide. And as takeaway, I would like to emphasize that the importance of this innovation process that can be very effective, involving the different parties in developing technology for electricity networks. So we met the TSO through a collaboration project, and we were able to know their issues of the real field. So this is the typical top-down approach to develop a solution, and we did it together with them. Then we approached the industry, which with this, say the provider, with this joint solution to find a way of bringing it to the field. This is the bottom-up approach, which takes advantages of the vendor experience in industrializing. And our contribution there was to provide a non-existing test environment using the hardware in the loop and the real-time HVDC modeling and simulations. So at the end of the day, we can consider SuperGrid as a catalyst in this process, and we are eager to find more case studies like this one or other ones to finally bring these applications to the real field. And so thank you once more for listening. Now you have a few 15 minutes if you would like to ask any questions now. Maybe you were really concentrated on the webinar, or it was very clear, but to now I have no questions on the subject. So I'll give some minutes. In the meantime, maybe I have an idea of a question for Juan Carlos. You did mention that DVAC can be also used in the multi-terminal HVDC networks. So, but you maybe didn't go much deeper on that. Could you just give an idea or explain how this can be done?
Yes, of course. Thank you, William. Yes. So, I mean, yeah, just for a little bit of the context, we know that the HVDC links they are operated in a certain manner in which we can provide a power reference to one of the converters, and the second one, through the control of the DC voltage, will evacuate the same amount of power, right? I mean, it compensates the losses, but at the end, it's more or less the same amount of power. What we have in multi-terminal DC grids, of course, it really depends on how the DC voltage is controlled. But let's say that if we have a classical voltage droop control in which the different stations participate to compensate a power reference modification or a power disturbance, what we propose to do, or what we have done in some other studies, we have some papers published in this topic, is that we can, through communication, of course, of the stations, we can coordinate the active power injections of those references to behave, for example, as an HVDC link between a pair of stations. We can coordinate two stations, so one station injects power and the other one absorbs the power. So we can have exactly the same behavior as if we had an HVDC link connected between those stations. So if we follow this philosophy, we can add either the angle difference control, we can add the power oscillation damping, we can add the fast compensation. And if we have multiple stations embedded in an AC grid, we can imagine that we can have several, let's say, virtual links connected between those pairs of converters. This is more or less the ideas we have managed to implement.
Okay. It was quite clear to me. Thank you. And we've received two more questions. So one is from Georgios Misiris. So thank you, Georgios. The question is, does the operating mode of a converter, say grid forming, grid following, affect the performance of the DVAC? And do you think that you need to adjust it due to different control modulations of the active power loop? Also, more general question, do you see grid forming implemented for an embedded HVDC link, or you see it more implemented for HVDC links connecting asynchronous areas?
Okay, so thank you, Misiris, for this, Georgios Misiris. This is right. Thank you for this question. Yeah, this is something we have thought about it, and both of your questions are really related. So yeah, maybe we can start by explaining how we see grid forming. So grid forming, of course, is a way to control the converter. It is mainly a way to synchronize the converter to the grid via the power measurements, and so we don't use a PLL. I mean, there are many different kind of grid forming controls, but at the end, this is how I understand it. The converter synchronizes to the grid through the power oscillations, and we act as a voltage source, right? So I say this because I think we can decouple two things. One is this power synchronization, and the second one is inertia. So inertia is not really inherent to grid forming control. We can adapt the grid forming control to provide inertia, of course, but if we provide inertia, we need a source of this inertia, right? Inertia also means that if we modify the power reference of the converter is going to react slower, right? This is also kind of intuitive. Grid forming is a good solution, of course, to provide inertia, but also to provide system strength for converters that are connected to weak grids, right? So in an embedded HVDC link, let's imagine that, for example, we have one station in grid forming and the other one in grid following. This is maybe a configuration that has been studied. You have a grid forming that is fast, meaning that it doesn't provide inertia. This converter that reacts fast to the power set point, we can apply the DVAC without, let's say, without any problem or without major problems, right? Because your converter is going to react fast. It's going to be controlling grid forming. It's going to react fast to provide DVAC capabilities, but it is not going to provide inertia. And this goes directly to the second question. If we have an embedded HVDC link, do we really need to provide inertia with this embedded HVDC link? Because if we provide inertia in one side of the HVDC link, this energy has to provide from the other station, and at the end they are both connected to the same AC grid, right? So I think this is an important question. I mean, for answering the second one, from my point of view, I think it really depends on the case. Grid forming is a good solution when we connect converters to weak grids. So I think in the future, yeah, grid forming is going to be used in embedded HVDC links also, especially for the station that is connected to the weak grid part. but maybe not with a lot of inertia. This is my feeling. However, if we have a supplementary source of energy, for example, embedded storage or storage in the DC grid, it can be possible to provide grid forming and inertia. I don't know if I answered the question, if I extended too much, but this is how I see this topic.
All right. So, Giorgio, thank you for the answer. You have another one that is, have you considered active and reactive power modulation? This by Joseph People Zadesh.
Okay, thank you very much for this question. Yes, actually, in the INELFE HVDC link, it has been reported that the reactive power modulations can provide also some benefits, especially they are related more to the power oscillation damping. I am not certain that we can provide synchronizing power. We cannot emulate the behavior of the active power of an AC line, which is finally the one that synchronizes different areas through reactive power. But also I think we can, let's say, apply some fast power compensation in a little extent with the reactive power. Also, which is very important to understand, is that the topological situation of the HVDC link will determine if the reactive power is useful for damping the oscillations or not. If we are connected, let's say, an example, we are connected to the extremities of the oscillation, it is way better to use active power. However, if we are connected mainly in the middle of the oscillation, it can be better to use reactive power.
Okay, thank you, Juan Carlos. There is another one from Michael van der Straeten. In the real system, you have several oscillation modes. How do you define how many remote frequency measurements you need, and where to locate the frequency measurements for the frequency difference activation action?
Thank you. This is also a very good question. I think this is more related to the implementation. Of course, we have discussed with Red Eléctrica, and it really, I mean, firstly, it really depends on where. I mean, if the TSO has already implemented some PMUs, if they have already implemented some PMUs, we can use those that are already implemented, and then we can see if they are useful. Again, for selecting the location, I think it's quite straightforward. Also, the ones that represent better the oscillation that you are analyzing are the ones that will be more useful. Let's say that the extremities of the oscillations were, I don't know, between the south of Spain and the north of Germany. Of course, it will be better to use this kind of locations, right? So I think a phase of studying the system, the real system, is necessary to determine which ones are the best locations from the implementation point of view, but of course from the let's say the technical point of view.
Okay, thank you, Juan Carlos. One more from Joseph. So have the robustness of the POD controller be tested on various operating conditions. So this is national, for example, National Grid in the UK have various dispatch such as summer mean and winter peak, which are minimum, and winter peak, which are drastically different.
Okay, for the POD, of course, the operating point of the system will modify the, let's say, the eigenvalues of the system, so the oscillating modes. But what we have observed is that the operating point doesn't modify. I mean, finally, the eigenvalues are a structural, let's say, feature or characteristic of the system, which is very related to how the system is interconnected and how the machines are placed. However, yes, I think that it is necessary for any kind of control, not only POD. I think what we have proposed here, the angle difference controller and the frequency activated action and the trigger power compensation. All of them have to be tested in different operating points to test their robustness. So I think if we want to go to implement this, for example, in a pilot project in an existing HVDC link, a phase of studies has to be done in order to understand how this operating point can affect the control, and if the control reacts correctly on all these different operating points.
Perfect. Thank you, Juan Carlos.
Thank you very much for the question.
So from the audience, that's all questions. I would like to ask one more before ending this webinar. So for the part about HIL simulation to Antoine. So what do you see as the next steps on HIL simulations, and like, for instance, testing delays, or more about the material testing?
Yeah, of course. I think it's some topics that will grow with the needs also of the market. For now, in the inside, so in our platform team, we would like to have more, let's say, materials to test communication. For now, the labs is really, for example, in our communication protocol, we have only a local area network via a switch. And we only do, let's say, loss of packets and delay thanks to the simulation. The next step would have for both of these topics to have, for example, several switch, either several switch, either one switch separated with VLAN to have a more, let's say, realistic communication network. So to represent what will happen in MTDC grids. And we would like also to have, some materials and let's say, for example, there exists some switch that can emulate jitter, loss of packet, delays. So that's what for the communication part in the HL. For the controller, it's true, we would like, and I think it will go on the way with as soon as we do this kind of while we will do this kind of project, more knowledge about what, let's say, make a controller resilient, to loss of packet. There is a lot of, we learned a lot with GE Digital on this subject with the phasor controller, to have all this metadata. For me, when I see an algorithm like that, that it is a 20% block of control to make the algorithm work, and 80% block that make it resilient, And I think there is a lot of work and knowledge to learn in HIL about this kind of topic.
Yeah, can't agree more with you. Thank you, Antoine.
Thank
you. And so I officially end this webinar now. Thank you for listening, and I hope to see you soon in next webinar chapter, or maybe collaborating in some exciting project. Thank you very much. Bye to everyone.
Thank you. Bye.
Thank you. See you.